this is our last lecture slash lab, and I guess for the rest of the afternoon you'll have time to work on either some of the labs that you may not have finished yet already, or the bring your own project activity. Okay, so the last thing I'm going to talk about here today is some of the minutia of the packer and the minimizer. And both of these pieces of functionality live in core 4. So you remember that pose and score function live in core 3, and then chemical and confirmation live in core 2. And then this is sort of more advanced than either of these two, and depend on their functionality. Okay, so the two directories here that I'm going to talk about are core pack and core optimization. Pack is where the packer lives, and optimization is where the minimizer lives. First, I'm going to start talking about the packer. So we've had a little bit of an introduction to this. Tim talked about it yesterday. So the packer, its purpose is to optimize rotamers on a fixed backbone. The inputs to the packer are a pose, a score function, which is going to guide the packer and figure out what it means for the rotamers to be optimal. And then a packer task, which is this it's a class just full of options. And you guys have seen a little bit about how to, what a packer task looks like, and how to manipulate it through task operations. So the packer operates in 4 main steps. First, it figures out who all the neighbors are in the pose, and it creates a graph to represent the neighbor relationships. Then it sits down and builds all the rotamers that it's going to use. Then it creates what's called an interaction graph, which is not a terribly great name, but what it's meant to represent are the interactions between pairs of rotamers. So when I say pairs of rotamers, pairs of residues. So the nodes in this graph are residues, designable positions in, or designable or modifiable positions in the pose. And then the edges are the existence of an interaction between them. And in this step, when you create an interaction graph, you compute these two things called one-body energies and two-body energies, though you don't always compute the two-body energies in this step. And then the fourth step of packing is running simulated annealing. And in simulated annealing, what we do is perform rotamer substitution. So we have some assignment of rotamers to the entirety of the pose, and then we assign a new rotamer, and then calculate the change in energy and use the metropolis criterion to decide whether or not to accept or reject that rotamer substitution. All right, so all of these steps make sense only in terms of what happens at the very final step. And so I'm going to tell this story of how the packer works, starting from the end and going back to the beginning. Okay, so inside simulated annealing, inside the packer, we have just basically a pair of for loops. So we have an outer for loop. We're going to iterate over the number of outer iterations in this outer for loop. And then in an inner for loop, we're going to iterate over the number of inner iterations. At the end of the inner loop, we're going to change the temperature of the system that we operate at. But while we're in this inner loop, we're at sort of a fixed temperature. Okay, so what happens in here? So for each iteration through this loop, we pick some random rotamer from the set of rotamers that we have available. And then we compute the change in energy induced by putting the new rotamer at the position that it corresponds to. And so we compute that by taking the difference in energy from the total energy, given that we have this new rotamer, versus the total energy in the presence of the old rotamer, the one that was already at that position. And then given that change in energy, we're just going to try to figure out whether or not to accept or reject that substitution. And if we accept it, then we're going to write down some information about the fact that this rotamer is now the new rotamer is going to displace the old rotamer. We're going to update some bookkeeping information. So the picture here is, it's kind of down here at the bottom of the slide, is let's say I've got this phenylalanine rotamer at this position. That's the old rotamer. And I'm going to pick a new rotamer, which is this leucine at that position. That's an isoleucine, excuse me. And so what I need to do to figure out whether I should make this substitution is then compute the interaction energy that this isoleucine has with its surroundings. And I'll compare that against the interaction energy that this phenylalanine has with its surroundings. And that's going to give me the change in energy, the delta E. All right, so this is the main computation in the center of this this pair of nested for loops. Okay, so delta E. This is where the packer spends all of its time. The Metropolis accept or reject thing, that's very fast. The bookkeeping is very fast. This is where all of the time is spent. But let me drop back for just a second. Sorry. The other thing that I wanted to emphasize about this computation is so you get the energy that this phenylalanine has with its surroundings versus the energy that this isoleucine has with its surroundings. What you don't need in order to compute the change in energy is the interaction, say, between this tryptophan and this phenylalanine. This doesn't change based on the rotamer substitution at this position. So you don't need to compute that energy at all. So the very first thing that the packer does in terms of an optimization is treat the score function as something which can be taken apart and then compute only the portions of the score function that actually change as a result of a rotamer substitution. Abba?
Yeah, so you don't move those 4 residues there when you substitute an isoleucine.
Right. The isoleucine is, say, the only thing that's going to be changing in this rotamer substitution event. So it says for some fixed I and for some fixed J, we're going to consider this substitution, and that's the only substitution.
Is there an option in which you can move all the residues that are in the interaction graph?
No.
What?
No? Yeah. You could imagine an optimization routine that tries to do something like that, but it would be a very different thing than from what the packer does. The broad class of algorithms for trying to optimize rotamers on a fixed backbone includes rotamer update steps where you might try to change multiple rotamers simultaneously.
Yeah, I mean, this is sort of like a self-consistent field method, right? You're changing something, holding everything fixed, then going to another one, holding everything fixed, and just iterating around.
You can do self-consistent field changing all the rotamers at once, right? You could.
Yeah.
You wouldn't do it just so. And this doesn't examine all of the rotamers that are available at this position. It just picks. It's got a currently assigned rotamer and it's got this alternate rotamer, and those are the only 2 that it looks at. Okay, so this change in energy, as I said, it's a difference between. It involves only the portions of the score function that change as a result of this rotamer substitution. And that's describable in terms of what we call one-body energies and two-body energies. So the one-body energy for the new rotamer is going to be, say, the new Dunbrack energy. So you look up in the Dunbrack table, given the assignment of phi and psi to this particular position and the chi that I have at this rotamer, what's the energy that I get for that? And it's independent of, say, the positions, conformations of any of the surroundings. You just need one residue in order to define the Dunbrack energy. So that'd be an example of part of the one-body energies. But then we'll call E1, say, the sum of all of the terms that are one-body energies. And then the two-body energies would be the interactions of the new rotamer that we're substituting, the isoleucine in the previous example, with all of the surrounding neighbors. And that surrounding neighbor list will be given by the edges in a graph. So that would be the two-body energies. And so the new total energy then you can think of as just being described as the interaction energies of all the rest of the background, plus the one-body energies of the new rotamer, plus the two-body energies of the new rotamer with its surroundings. And then for the old rotamer, you maybe already have this information, but you also have its one-body energies, and you also have its two-body energies, the interaction energies of the phenylalanine with its surroundings, the Leonard-Jones, the solvation energies for that phenylalanine and its surrounding residues, and then also its one-body energies, its Dunbrack energies, and things of that form. So that the total energy for the system when you have when you have the old rotamer that's the sum of the interaction energies of all of the background, all the rest of the structure with itself, and then the one-body energies of the old rotamer and the two-body energy of the old rotamers. And so all of the, so you have the total energy would be some term I'm not describing here, minus a term that I'm not describing here, and then it just sort of falls out. And what you're left with is just the difference in one-body and two-body energies for the new rotamer against the one-body and two-body energies for the new, make sure I said that in the right order. First is the new rotamer, and the second is the old rotamer. Okay, so and then as I said, this is what we spend almost all of our time computing. And so one of the first things that oh, I have more text here. Oh yes, I forgot one of the components here, which is maybe worth mentioning, which is that the one-body energies include, say, the internal energies for each residue, and then the interaction energies that the new rotamer would have with the background, which may be fixed and is not part of the packing simulation. You can have, well, there's certainly the backbone, and you can have the Leonard-Jones interaction with the backbone that's not moving. But there's also other entire residues that you can disable during packing that you just consider part of the background, and they're fixed. And the interaction, the two-body interaction energies with those residues would get folded into the one-body energies. And then similarly, and as I've already said this, the two-body energies are all the two-body energies with new rot has with a neighboring rotamer J. And so the first optimization that people considered in the packer was to take these tables, to take these energies E1 and E2 and compute them ahead of time and store them in big tables. And so this would be, say, a one-dimensional table, and this is like a two-dimensional table. So this would have one entry for each rotamer, and then this would have one entry for every rotamer pair between the position that's being substituted and the neighboring position. And so if we have a sparse set of neighbors, then the appropriate data structure in which we should store these E1 and E2 tables is going to be an interaction graph. And so, or is it going to be a graph? And so that introduces an interaction graph. So if we replace all of the residues in this structure with nodes, and we can add edges between every pair of interacting residue, then we can just sort of ignore a lot of the other things. And so that is, we don't necessarily need to represent what the original assignment of rotamers was when we came into it. We just think of this as designable positions or repackable positions. Okay, so the nodes in this graph, they record the number of states that they have available. So if residue 2 has 100 rotamers and residue 3 has 300 rotamers, then you would have different pieces of information for each node. And then you would have an array of one-body energies that's stored on the nodes themselves. And it's going to have an array, each node is going to have an array with num states entries. And then for the two-body energies, those will be stored on the edges. And it's going to be a table of size node1 dot num states times node2 dot num states. So it's an n by m table where n and m are the number of states for the two nodes respectively. And then I guess one final optimization you can think of is that since you're going to be subtracting the old rotamer energies as you're computing this delta energy from the situation, from the so in order to get delta E, you have to subtract the old energies from the new energies. And in order to get the old energies, or in order to get the old rotamer, it had at some point had to be a new rotamer and then get accepted. And so when you performed the lookup, you can actually cache the old energies. And these energies are stored on the nodes. And so that makes an energy table lookup a little faster. Right, so when I need to compute the new rotamer energies, then it's a matter of looking up the one-body energy on the node for new rotamer, and then the two-body energies in the table for all of its edges. And so it's just a simple edge traversal for a single node, and then a lookup at each one of those edges. And that's really the core of packing, is making this computation as fast as possible. And it's just like, it's a difference. It's really, I mean, like the mathematics behind this are like sadly simple. It's unimpressively simple. But somehow my committee didn't notice this and I was able to graduate. Yes?
What's the difference between the num states and the num states entries?
I'm saying that the number of entries that this array has is num states.
Okay.
Yeah. Okay, so part of so in order to perform these calculations rapidly, in order to make the packer very generic, so that it can compute the one-body and two-body energies, we have this abstract interface between one-body energy methods and two-body energy methods, so that if somebody comes along and wants to add a new score function or a new term to Rosetta, they can do so by defining if it's a one-body energy, then they need to define a new residue energy function. Or if it's two-body energy, then they need to define a residue pair energy function. And once they do that, then they'll just activate their scoring term in the score function and hand the score function into the packer, and the packer will use their new energy term to compute the two-body and one-body energies. So that means that the packer is like remarkably stable in terms of like edits to it. People aren't constantly changing the code. This makes my life a lot easier, because the more people that are editing the packer, the more bugs get introduced. So this is a good argument here for polymorphism as a way to have a section of code that you can rely on without it changing, but still have it do different things as needed. Yeah. So so the common way of figuring out, or populating these tables that would go on the edges in the interaction graph is to just iterate over all pairs of rotamers and evaluate the two-body energies for them. So I'll give a little plug-in or a short description about this try versus try algorithm, which I have implemented in Rosetta 3 as a templated function. It's a little difficult to set it up if you were interested in, say, writing a new term that depends on atom pair energies, but it's entirely possible. And the advantage of this algorithm is that it makes things faster, and the way it speeds things up is by sharing the expense, or if you have two atom pairs that appear in multiple rotamers, then you can compute the atom pair interaction energy once and then reuse that for multiple pairs of rotamers. So the easiest example of this is if I'm placing a serine and I have, let's say, 12 serine rotamers. The C beta is in the same place every time. And so I've got these 12 serine rotamers, and maybe I've got 12 phenylalanine rotamers, and the C beta for all those phenylalanine rotamers is also in the same place. So I can get the C beta interaction energy, compute that once, and then reuse it then to calculate all 144 rotamer pair energies. So you can get a speed up in that sense. You can also figure out pretty quickly whether two pairs of atoms are far enough apart such that they wouldn't interact, and then none of the other atoms in the rest of the rotamer would interact either. And that gives you a further speed up. And this is currently used by the Leonard-Jones energy, which is also known as the E-table energy, the hydrogen bond energies, and the Hack-Alec energy. If you have a term you're developing that requires atom pair energy evaluations, then this could be useful for you as well. Abba?
Well, what is
It's a Coulombic potential with a distance-dependent dielectric, and so it's set up so that you define some cutoff distance, and it so if you have like a cutoff distance of 12, then there's some very small energy that you have at 12 angstrom separation, and you just subtract that whole thing and shift up the whole functional form by a little bit so that it goes to 0 at 12 angstroms. So we have that same thing. But then to smooth it, I put some splines or some polynomials. Like they're not splines because they're not long, but to ramp smoothly to 0 here. And then as you get two atoms that are very, very close together, you get a singularity in the Coulombic. So for attractive, you get an infinite. I guess if they're opposite charges, you get infinite energy. If they're like charge, or I said that backwards. Anyways, so there's a singularity at a distance of 0, and there's kind of an overlap between Hakelek and the hydrogen bond energy. So in order to keep those separate, we ramp Hakelek to a constant value at some parameter. It can be fixed or set from the command line with a set of flags. At like 1.6 angstroms.
Oh, and then H flag takes over. Right?
Yeah.
So should we use that flag?
It looks like it. There's actually going to be an energy function meeting where I'm guessing we're going to decide on.
Okay.
We're going to at least talk about the energy function, but maybe we'll like say this is the new default score function. Maybe, I don't know. I'm optimistic. We'll see what happens.
To be a little bit stronger statement, we've recently shown that using the Hakelek with our new reparameterization of hydrogen bonds improves in every benchmark at least the same. So
That's awesome.
we basically it's ready for use if you want to try it, but perhaps it might get integrated with other corrections that we will.
What flag do you use to improve H flag?
Corrections, SP2 correction. I sent out an email to the list.
You will H bond underscore SP2 underscore correction.
I can send it out again.
It's in namespace corrections. So you dash corrections : and then it's sp2 underscore. Tell me again. Well, why don't we just send out the email another time?
That would be really helpful.
Yeah.
Okay.
Yeah. Okay. So right. Some other details of the packer. One is that this. So this is the center computation, this delta E computation, in this standard scheme where you have this table E2 for each edge in the interaction graph. The primary expense of this is a matter of just basically you can't fit the whole interaction graph into memory, and so you have a cache miss for every time you pull down one of these entries in these tables. And cache misses aren't the slowest thing in the world, but they're not great. But anyways, that's primarily what the optimization for is in when you pre-compute. But the memory use is considerable. So let's say you've got 20,000 rotamers over 40 positions. This is a modest design problem. And let's say it's spread out enough, say across either side of an interface, such that you only have 300 edges in this graph. So if there are, let's say in this hypothetical example, 500 rotamers per node, then each edge is going to have a 500 by 500 table. And if you multiply just the expense of the tables out, you're looking at 283 megs. So this is a pretty big data structure pretty quickly. There's a little caveat here, which I think is hidden. Can you just go away? I don't know how to get rid of that, but it's under there, and it says something like, "Oh, it's not even there. Never mind. It's not Google's fault." There is actually a sparse representation of the contents of this table. I'll get to that, I think, on the next slide. So it's not maybe as bad as 283 megs, but it's a large amount of memory. In the second scheme, you can compute rotamer pair energies on the fly. And store some, but maybe not all. So in the same test case, if instead of storing one table 500 by 500, you store 2 tables of 500 by 10. So if you think about the square of 500 by 500, there's like this portion of the square and then that portion of the square. And I guess you might wonder what those 10 positions are. I'm not going to go into that terribly much. I have a paper on it if you're really curious. This actually, so it cuts down memory use considerably. So if you're on a system like a Blue Gene where there's very little memory and no virtual memory, and you really want to perform design, then this will save you a significant amount of memory. And the scheme is called this linear memory interaction graph. Tim hinted at it a bit before. You can activate it with this flag linmem IG 10. 10 is the recommended number here. It's what corresponds to that 10 there. It has some pretty nice features to it for design. A drawback is that, let's see, so if you want to compute an interaction graph and then run simulated annealing like 20 times and reuse that interaction graph over and over again and see like what different packings you can come up with, then it's faster to pre-compute all the pair energies and store them. If you're going to repack a structure, say in the middle of relax, and you're not going to add EX1 or EX2 rotamers, or you're not designing, then it's faster to pre-compute and store. But besides those cases there, the linear memory interaction graph actually performs faster than the pre-compute and store option, and it does so using dramatically less memory, making system admins a little happier if your jobs are running on their machines. And the reason for this is that during packing, it turns out you don't have the chance to look at all of the pair energies that you compute. So starting off and computing all the rotamer pair energies and then storing them and then not looking at them, you waste a lot of time in this setup and storage here. And so that means that if you only store some of them, say discarding them after a little while if they go stale, in this linear memory interaction graph scheme, you can save time and memory, which is kind of a win-win. But I'll remind you that there are some exceptions, and so the decision has been not to make the linear memory interaction graph default. So if you're designing, I highly recommend either incorporating this flag into your protocol, like hard coding it if you have like a new mover that's going to do some design, or activating it from the command line, and then making sure that your packer task has an initialize from command line task operation. I did say that on the previous slide that we have this sparse table representation that actually reduces the memory use just a little bit here. It's mildly interesting, so I'll describe it. But basically, we organize all the rotamers for this table by amino acid. So all of the rotamers for aspartate are going to appear right next to each other, like in order. I mean, they just have some index that's assigned to them, like 1, 2, 3, 4. And then for glutamate, we'd have another block, 5 through 20 or something. And this describes like all of the rotamers that we would have available. And then we can figure out, based on how big each of these amino acids are, whether or not, and then how far apart their C betas are, whether they're going to have any interaction energy or not. And most edges in the interaction graph are long, like they're from residues that are just barely in contact with each other, for the same reason that Jack talked about this morning, that you have this growing, like quadratic expected distribution of hydrogen surrounding an oxygen. Like the space just gets larger. And so you can figure out that a very large percentage of the values in this table are going to be zeros. And so if you know that up front, then you can say not allocate space in this table for the sections that are going to be 0. And so pictorially, it would look something like this. If you were somehow able to allocate memory such that this was somehow not there, then it would look like that. But really, you just have to rearrange this table quite a bit. So in this case, I've chosen the amino acids that are kind of smaller, or the pairs that are smaller, and they, like say this aspartate and this histidine, let's say they're too far apart to interact, then again the aspartate and histidine on the other residue would also be a. Anyways, so this saves about, so if you had in this previous calculation 283 megabytes, it's like a 40% reduction. So if you multiply this number by 0.6, that's how much memory we would use on average. Okay, so that's now steps 4 and 3 in how the packer operates. And the previous step to this is building the rotamers that are going to be used inside of the rotamer optimization. And so there's class rotamer set, which is going to hold all the rotamers for a single residue. And then there's class rotamer sets, which holds an array of rotamer set pointers. And this array is going to be of size, or it's going to have as many entries as there are designable or repackable positions in the pose. And the difference, and it's a little confusing, I'll give you that. You just have to remind yourself that there were two movies, Alien and Aliens, and they were different, and you can get into arguments over which one was better. Okay, so we call the residue positions where we're allowed to redesign the molten residues, and there's some mappings back and forth between, say, this size would be of total residue, and you could ask, so I know the residue like position 10, what molten residue is that? And that would be molten residue 1, for instance, if you weren't packing residues 1 through 9. And so similarly, there's an array of size n molten res to res ID, which would map back from molten res 1 to position 10 in this hypothetical example. Oops. Oh yeah, so there's that count of the number of molten residues. That's part of it. Okay, so then you have this count of the total number of rotamers that are in the system. That's the sum of the number of rotamers for every one of the repackable positions. So this might be something like 20,000 that I threw out in that previous example. In the middle of packing, you often ask for a random rotamer, and that's chosen currently by picking a uniform, or picking from a uniform distribution between 1 and the total number of rotamers, so between 1 and 20,000 in this case. And then, so I mean, if you want to think about that a little bit, it means that if you've got one position with like 10,000 rotamers and all the other 10,000 rotamers are spread over the other 50 positions or 39 positions in that previous example, then you would spend roughly half of your time considering rotamer substitutions at that one position with 10,000 rotamers. So that's something that may or may not be interesting to you. It may not be the most efficient way to go about optimizing the structure. Okay, so let's see. So there are a couple more vectors here that I'll tell you a little bit about. I bring them up because mapping back and forth between different enumeration schemes is like a very common way to optimize your code, like to have vectors of indices to other vectors. It makes it so that you can walk through memory pretty quickly and efficiently. And so this is one mapping back and forth between two different sort of enumeration schemes. Here we got a vector that stores the number of rotamers for each molten res. And so if you summed the contents of this vector, that would give you the total number of rotamers and rotamers. And then this is an offset vector. So this says what's the first rotamer number for each of the molten residues. And so for molten residue 1, this value would be 1. And if molten residue 1 has 100 rotamers, then molten residue 2's offset would be 101. So that would be the starting position. And then it's nice to be able to say, like, if I have rotamer 10,024, what residue does that belong to? And that might belong to molten res 39 or something. Yeah, this is the data that the rotamer sets keeps intact. In addition, there's data that's held inside this class rotamer set, which has itself defines a whole bunch of virtual functions that are all abstract. And then it has a concrete derived class from it, rotamer set underscore, which actually implements all of these virtual functions. And it's kind of hidden from main interaction. So you mostly interact with this interface class. We don't do a whole lot with interface classes in Rosetta, but this is how it ended up getting implemented initially, and it kind of stuck. Okay, so rotamer set represents all of the rotamers for a single position, and it does so by holding a vector of residue ops. So each rotamer is represented by an instance of class residue. So class residue, I'll remind you, has like the conformation of a single residue. It's got the XYZ coordinates for each of the atoms, and it's got a pointer back to the abstract chemical information that's held in class residue type. So you can ask a residue, so like how many atoms do you have, and that's stored in the chemical, the residue type object. And you can ask the residue for the coordinates of particular atoms, and that's held in the residue object. Let's see. So there's a count of the number of different residue types, and then there are a set of offset arrays and number of rotamers for each residue type. So these help you map back and forth between, if you have a rotamer, what residue type does it come from? If I've got a residue type, where do the rotamers for that begin in this enumeration? Oh, excuse me. Is this one on? I'm going to go with this one. Similarly, there's a separate piece of data which is very similar, which is the N residue groups, where you have information about the beginning position and offset array. Where does the first rotamer of a residue group begin? If I have a residue group, then how many rotamers does it have? And if I've got a rotamer, which residue group does it belong to? The difference between residue types and residue groups is that all the rotamers with the same residue type point to the same chemical residue type object, and all the rotamers in the residue group have to be roughly equivalent, which means that they need to have the same size. So the neighbor radius needs to be the same, and they need to, I think, correspond to the same amino acid. So basically, this is a little bit of a hack so that we could have the number of residue types, which is going to be 21 if you're going to design all amino acids, because we have two different residue types for histidine, one that's protonated on ND1 and one that's protonated on NE2. And then 20 different residue groups where you've taken histidine and pushed it together. And that's useful for some things that I'm not going to talk about. But if you look at the number of residue types versus the number of residue groups, that's what's going on there. So okay, then the question is, how do you actually build your rotamers? And in the main class that's responsible for this is, or the base class that's responsible for this is the single residue rotamer library. It implements or requires that derived classes implement this function fill rotamer vector. And you see that it takes a whole bunch of const data. So that's just information about how it's going to build its rotamers. And then it takes a non-const reference to a rotamer vector. And so you can see from the interface that what it's going to do is modify this rotamer vector. In fact, that's what it does. So it has a pose and a score function, and it's got the task that describes the rules for building rotamers at this position. It's given this neighbor graph, which tells it who the neighbors are, and that'll be useful. I'll describe in just a moment. It's got the residue type that you're actually going to be building. So this might be, like a phenylalanine residue type. It's got the existing residue, which might be a leucine that was already at that position. And then it's got some description of how to take the rotamers that you would build and diversify them by stepping to the left and the right for each of their chi dihedral angles by some amount given in these vectors. One Boolean to tell whether or not that residue is buried, and then it's supposed to write its output here. There are a couple different classes that derive from single residue rotamer library. We have a generic Dunbrack library, single residue Dunbrack library class, from which there are two derived variants. A rotameric single residue Dunbrack library, which is used to represent the rotamers from the 2002 library, and then the semi-rotameric single residue Dunbrack library, which is responsible for representing the residues whose terminal chi's have an sp2 hybridization at the third atom. So this is 8 of the 18 rotameric residues, so phenylalanine, tyrosine, tryptophan, some of the other ones there. And so both of these are able to fill a rotamer vector with rotamers as needed. Similarly, you can have a single ligand rotamer library. So if you're working with ligands and you want to have multiple ligand conformations and switch between them in packing, then you can provide, there's actually like a multi-model ligand conformation input that will allow you to align the initial models that are in that PDB with the initial the input conformation of the ligand when you enter packing, and that's so that's really convenient if you want to modify the conformation of your ligand in the middle of packing. Okay, so I told you that one of the arguments to the fill rotamer vector is this Packer neighbor graph, and that's used to figure out if there are rotamers that collide with the background. And so and what we do is we perform this bump check test. And so we compute the Leonard-Jones interaction energy of every rotamer against the backbone, and then against the side chain of those positions that are not changing inside the Packer. And having the Leonard-Jones energies, we throw away rotamers that collide so badly that there's no reason to even consider them during the rotamer optimization phase. And that means that the rotamer set requires this neighbor relationship, so it can figure out what are the neighboring residues. And that's given in this first stage of packing, which is just neighbor detection. And so at this point, all we do is we figure out for every pair of residues I and j, whether any of the rotamers that would be built on I could interact with any of the rotamers that are going to be built on j. And remember, we haven't built rotamers yet at this point. And so the way that we figure this out is we look at all the different amino acids that could be placed at I, and we look at the neighbor radius for those atoms. And we look at all of the amino acids that could be placed at j, and we look at the maximum neighbor radius for those amino acids. Sum that up, and we sum up that with the atomic interaction cutoff in the score function, and that gives us a threshold by which we can figure out if 2C betas are within that threshold, then they need an edge in the Packer neighbor graph. Okay, so those are the 4 steps of canonical packing in the pack rotamers function. It turns out that there are lots of different ways that you can formulate the packing algorithm. You can try to optimize all the rotamers simultaneously, and in that we talk about this function called pack rotamers, which I just described. You can optimize them kind of greedily by, say, taking all the positions that you're going to repack and then looking at one at a time, building the rotamers for that position, and figuring out what the best rotamer is given the current assignment of rotamers to all the other positions, and then just going with that best rotamer. And then you go to your next residue, pick sort of in random order. So you're not going like 1 to n when you're doing rotamer trials. You just skip around through the pose. So these are both discrete ways of optimizing rotamers. There are actually 2 continuous ways of optimizing rotamers as well. So RT-min is the continuous version of rotamer trials, where you're going to optimize one rotamer at a time. But before you decide what the best rotamer is, you're going to optimize. You're going to run minimization for each of your rotamers. So you minimize them in the current context, and then you pick the best minimized rotamer from that set, and you assign that to your pose. And then the continuous version of the pack rotamers algorithm is minpack, where you optimize all rotamers simultaneously, as is in the discrete case, but at each rotamer accept reject decision, you first minimize the rotamer in the current environment, and then you do the metropolis criterion. The minpacker is slower because it performs minimization, but it's a little faster because you don't have to build as many rotamers to get low energies. So you don't need to have, typically we run pack rotamers with the EX1, EX2 flags, at least in design, maybe not in the case of relax. But in design you run with EX1, EX2, and so you build a lot of rotamers, and you run a lot of rotamer substitutions. And in the minpacker you don't need EX1, EX2, and so you perform, actually I'm not going to say that you perform fewer rotamer substitutions, but you have many fewer rotamers. So the minpacker is, has quite a lot less memory overhead, like a factor of 9 if you compare it against EX1, EX2. And your interaction graph, because it can't really cache data efficiently, so it doesn't even have that 11 meg overhead that the linmem IG would in that hypothetical example from 8 slides ago. If you're finding that you're really running out of memory, but maybe you've got a lot of time on your hands, then check out the minpacker. The minpacker unquestionably gets lower energies than pack rotamers. It's I can't remember what the offset is, but there was never a case when I was testing it where the minpacker got worse than pack rotamers. Maybe that's not surprising. It also gets a lot lower energy than if you run pack rotamers, and then after you finish pack rotamers, run minimization on all of the on the final assignment of rotamers in there. Okay, but so I'm not going to go into the details of RT-min and minpack yet, because I haven't told you anything yet about the minimizer. I'm going to be a little bit briefer on the implementation of the minimizer, but I'll go into some of the details of the math. And there's this great paper from '84 that I'm going to walk through, but which I guess this was before papers were published with figures, is basically incomprehensible, and there's no drawings on something which clearly requires a drawing to be understood. So I'll give you some drawings with that too. Okay, so in the minimizer, the input to the minimizer is a pose. It's a score function, a move map, which describes which of the degrees of freedom you would like to allow to change during the optimization process, and then the minimizer options. And then you would pass this, say, to like the atom tree minimizer. You pass these 4 things, and you can tell it to run, and it would go 2. Internally, the atom tree minimizer, it creates a thing called a minimizer map. It initializes a minimization graph. I'm not going to talk about that yet, but we'll see a lot of this guy. And it utilizes this multi-func. So the minimizers are all generic enough such that you can give it any kind of function that takes, say, it takes a multi-vec. A multi-vec being a vector of reals. So think of that as 20 arguments or something, or maybe 50 arguments. Those would be the function parameters. And then the minimizer will ask for the derivatives and the value of the function given those input parameters, and try to minimize it accordingly. And you can give anything you want to the minimizer classes that we have, including, say, an atom tree multifunc or other kinds of multifuncs. And then there's the minimizer itself, which has implemented within it 8 or 10 different optimization algorithms. Okay, so in Rosetta, we typically minimize our structures with respect to internal degrees of freedom, and in particular, the dihedral angles of the system. And that gives us this really convenient property that we don't have to worry about bond angles and bond lengths. Those will just remain fixed through the course of the minimization. One reason that we wouldn't want to worry about bond angles and bond lengths is that they change very rapidly over a very small chain, so for atom pair distances, so the function changes rapidly for a small change in the conformation of the atoms. So if you have like an angle, that changes somewhat rapidly. If you have let's say a bond angle, that is, in the energy function, that changes rapidly. If you have a bond distance, that changes extremely rapidly. So you just move your atoms a little bit, and your function is incomprehensibly high. So that means that the energy landscape for such a system is constrained mostly by the changes in the derivatives for the bond lengths and bond angles. So in MD, you have to perform femtosecond time steps because if you try to project out longer than that, then the bond angles get stretched, the energy goes through the roof, and then they come back together, and then you have sort of this numerical instability as your atoms jump back and forth until the protein explodes.
Vibrational frequency of hydrogen.
Yeah, yeah. So it's this aliasing problem where if you try to sample a high frequency distribution at low resolution, then you get this odd behavior. Okay. Yeah.
Terrible.
Yeah. So we work in idealized bond angles and distances, and primarily, we don't always do this, but we primarily do that. And then we have this challenge then of computing the change in energy with respect to, say, the distance between two atoms, alpha and beta, into some change in energy due to this rotation about some dihedral phi. And this math is actually kind of tricky, and is solved very elegantly in this paper by Abe, Braun, Nagudi, and Go. And yeah, I recommend you take a look at it. So I'll go through the math that's in this paper, or the math of the first half of it. They cover the rapid calculation of first and second derivatives, and we don't use the second derivatives in Rosetta. We just do first derivatives, and then we get our Hessian numerically. Okay, so this is the picture that's used, that's referred to in this paper, but is never drawn. So you have two atoms, alpha and beta, and you have their coordinates r alpha and r beta, and there's some interaction energy that these two atoms have. And then you've got some bond vector, some axis of rotation A. So it's awful, A and alpha, but yeah, that's what they do. So A is this vector about which you're going to perform some sort of torsional rotation. And as you rotate about this axis, you're going to swing R alpha, you're going to swing the alpha atom through space around this circle. So if you project up this axis here, you get the center of the circle, and you're going to swing R alpha around in space. And you want to figure out now what the change in the torsion here is going to do to the interaction energy between alpha and beta. Okay, and then there's some labels here, which is that they talk about the beginning coordinate for A and the ending coordinate, and they use beta sub A for the beginning and epsilon parentheses A for the end. I don't know why they need to mix beta in twice in this equation, but they do. What's nice, though, is that beta of alpha I don't think appears through the rest of their math, so we don't have to worry about that. But this end coordinate, epsilon of alpha, does. Okay, so those are the players here. Now, so we're going to continue a unit. So we're going to think about a unit of rotation about this axis A. And so we need to think about the vector that connects epsilon alpha to R alpha. Excuse me, epsilon A to R alpha. So that's this vector R. So it's, I guess, the distance between them. And then if you measure this exterior angle from beta alpha epsilon, beta A epsilon A to R alpha, this angle here, or maybe the interior angle if you consider the center of the circle, call that theta. Then the length of this circle in space through which R alpha is going to move is R sine theta. Okay. We need to talk about two vectors here. The vector Q alpha beta, which points from alpha towards beta, and then the vector E sub A, which lies along this axis from beta of A to epsilon of A, and is of unit length. Okay, so here we are. Okay, so we need to ask how much does a unit of rotation about axis A move, or how does it change the distance between alpha and beta? Okay, so if we performed 2 pi rotation, if we rotated about A by 2 pi, then we're going to move alpha 2 pi r sine theta angstroms around this circle, which means that for any 1 radian worth of rotation about the circle, we're going to move by 2 pi r sine theta. Excuse me, did I get that right? I feel like 2 pi drops out. So the circumference of the circle is 2 pi r sine theta. So per unit of radian rotation, then r alpha moves along r sine theta. Okay, so that's what I need. So r sine theta is how much r alpha moves. And then now if we want to know the change in the distance between r sub alpha and r sub beta, so this is the vector that points between them, and the magnitude of this vector, the distance basically between alpha and beta, based on the amount of rotation about the axis A. That's given by the dot product of q alpha beta times the cross product of EA and R alpha minus EA. Okay, so that's going to give us this orthogonal. It would, if you took this cross product, it would be orthogonal. It would be sort of into the plane of the board here, right? And then I'm going to take the dot product of that motion. Sorry, is that where it's going to be, or is it going to be coming straight up? I'll do the right-hand rule of R alpha times EA times R alpha. Yeah, can't do the right-hand rule while on camera, but I happen to know that this is true. Okay, so so now we have the amount of motion that you get as a function of this vector and of that vector and of that vector. Okay? Yeah.
Okay, well, maybe I shouldn't stop you mid-explaining. Doesn't this seems like the perfect place to use quaternions? Because you can just multiply the quaternions for each, like if you can just propagate off the rotation, and you operate on the vector between atoms. So if you have a certain quaternion that represents that rotation about that bond, if you multiply that to the R vector, it would turn your atom.
Right, but that's not what we're going to do.
Okay.
Yeah.
Okay.
What we're doing now is trying to figure out the derivative of the energy function with respect to a change in this torsion.
Okay. Okay, so you're trying to
Yeah.
get a representation that you can take the derivative of?
Mhm.
Okay, well, never mind.
Okay, so all right, so we have this function now, the change in the distance between these two atoms as a function of the rotation about this axis A, and we can compute now the change in energy with respect to this the rotation about axis A by multiplying the change in distance by the change in energy given the change in distance, or the change in energy as a function of distance. So we have, if we can evaluate our energy function to tell us the distance is a function, the energy is a function of distance, or the derivative is a function of distance, and then multiply it by this term, then we get the derivative of the energy based on the rotation of this axis. Okay, so that looks like this. So we have dE, dr, that we're just going to compute from our energy function, like the Lennard-Jones energy function that's just analytic. and then we're going to multiply it by the term that we had from the previous slide. Okay, so we have E sub A and the cross product with the vector from EA to R alpha. And then we'll multiply that by this vector here, Q alpha beta. Okay, so the challenge here, or the problem with this representation, is that if we were to sort of naively take this math and then try to go and compute the energy, the derivative in energy with respect to the torsions, we have this problem of joining together all the torsions that are in our system and all the atom pair interactions. So we have the torsion represented here and then the atom pair interaction here, and they're all just jumbled together. And so if we had n DOFs in our system and m interacting pairs, then we'd have order nm computations to perform. So we're this is a lot of computation, right? Because the number of atom pair interactions in our system is going to be very large, and the number of torsions, even if it's not huge, we don't want to multiply that by a huge number. Okay, so the rest of this math is about coming up with an algorithm that makes this faster. All right, and so the goal is to somehow separate out the information about the torsion from the information that relates alpha and beta. Okay, so let's go from there. So we're going to take Q alpha beta and replace that with the normalized vector R beta minus R alpha divided by the norm of R beta minus R alpha. So that's a simple step. And then we're going to distribute the dot product. So we have now E alpha cross R alpha minus R epsilon sub A. Take that with the dot of, we're going to distribute the cross product. So this R beta minus R alpha is going to appear twice, and then we're going to have R alpha in this portion of the difference, and then epsilon A in this portion of the difference. So we have this cross product and that cross product have been distributed from here. Okay, and then down at the very bottom of the slide, we've got now let's see what happened here. We distributed. This is sort of the best step here, which is that we've got this vector. I believe the name is the vector triple product. So it's the cross product. Cross product of two vectors and taken with the dot product of another can be rearranged so that it turns into the dot product of one vector with the cross product of two other vectors. And we've left this portion of the summation the same. All right, so I'm going to go to the next slide and make things bigger. All right, so we had that vector triple rearrangement here. So and then I'll just distribute the cross product. So we had R beta minus R alpha taken with the cross product of R alpha before. And so distributing that, we get this term. So R alpha minus, or cross product with R beta. And then we'll subtract off R alpha cross R alpha. And that's 0. So that's nice. And then this term was the same from the previous slide. And then finally, we're left with this statement here. So we have the dot product of EA with this cross product, and then you subtract also the cross product of EA with the dot product of these guys. And what's nice is that we've now separated out EA from the two interacting pairs. I'm sorry. So all the terms that depend on the torsion. So EA and epsilon of A. These are separated out now from the terms that depend on the particular atom pair alpha and beta. So now that we just have a dot product of this thing with this guy that depends on alpha and beta, and a dot product of this form with the cross product of alpha and beta. And so that's the magic here. So now we have axis A separated from the pair alpha and beta, and this is going to give us this order nm algorithm. And it needs to be explained in just a little more detail. Okay, so this was the math from the previous slide, I just shifted it up. So this is the same equation that I just said. And so if you take this portion here, r alpha cross r beta, divided by the norm of this vector, and then multiply by der, we call that F1 in Rosetta. So it's this cross product normalized by the length of the vectors times the change in energy as a function of distance. And then if you look at this term here with r beta minus r alpha divided by the norm of that length times the change in energy as a function of r, we call that F2. All right, so these are the two vectors that we compute when we're looking at energy functions. All right, so the recursive algorithm now is that you can sum up these F1 and F2 vectors through an atom tree that describes the kinematics of the system. And then once you've summed up all the all the F1s and F2s, then you can multiply them by the portions of the system that depend on the torsions about which you're doing your rotations. So you can sum up F1 and F2s, and then you can multiply by the endpoint. You do a dot product with this endpoint coordinate, and then subtract off this cross product taken here. So you can add up all these F1, F2s. And to do that through this tree, you can imagine that each node in this tree has space to store an F1 and F2 vector, and we're going to recurse starting at the root. We're going to descend all the way down. So we're going to iterate. We're going to call for child and node children, sum up the tree. So we're just going to go all the way down to the lowest atom in this tree. And then once we get, so we're going to be down here. So we call it for a leaf node in this tree. Leaf node has no children, and so it's going to iterate across, for atom and node controlled atoms, it's going to, right. I forgot to say that this tree is a tree of torsions as opposed to a tree of atoms.
What's that change?
What's that?
Which side change?
That's just a tree. It doesn't look a lot like anything protein-like.
Oh, yeah, I thought that was the backbone over there. No, that doesn't make sense.
Yeah, I don't know. I just started drawing at one point. Yeah, it's not very protein-like. But this algorithm doesn't require proteins, so it's generic enough. Okay, so the tree is of torsions. So let's say I get down to the, this is like the lowest leaf node in this tree. Then I'll iterate across all the atoms, and I'll sum up the F1 and F2, like the atoms that are controlled by this torsion. So that's going to be everything beneath the tree here. It's a change in this torsion. And I'll sum up the F1 and F2s for that. And similarly, when I get over, and then I'll return, right? And so at this point, if I get to this node, then I'll descend in this direction, and I'll eventually reach this torsion, which will say control these atoms. And so I'll see that this atom I is going to move, and so I'll get the F1, F2s from I. And so for the interaction of I and J, they have these equal and opposite F1, F2 vectors, so that as I sum back up the tree, the F1, F2s are going to cancel at the point where you get to a torsion that moves both I and J together. So they just like cancel out. So that's kind of sweet. So this green here is to represent that the yellow and the blue have merged. Sweet, and that's our minimization algorithm, or that's our derivative evaluation algorithm. The minimization algorithm, which uses these derivatives, then is more complicated. But it's when I say more complicated, I mean it's a separate thing, and I'm not going to talk about it now. There's more to it. It's complicated. I don't know that it's more complicated than this because I haven't studied it. But it may be very complicated. Okay, so yeah. All right, so the minimizer, I'm not going to talk about it in much more depth than I've already talked about it. How am I doing on time?
It's 4:20.
What time was it supposed to end?
Good question.
Okay. I think this is the second to last slide, so we're fine. Okay, so these are the inputs: the pose, the score function, the move map, and the minimizer options. So the minimizer map is going to hold an F1, F2 derivative vector sum, and it I think is going to hold one per. Yeah, it's got one per atom, and it's also got one per node in the minimization, the torsion tree. The minimization graph stores the residue pair neighbor relationships and is used by the score function to rapidly evaluate the score during minimization. So not all residues are moving with respect to each other when you minimize, and it's smart enough to evaluate only the interaction energies for those pairs that are moving with respect to each other. You can also cache data on the edges in this graph. So that's how the E-table stores its residue pair neighbor lists. It caches them on the edges in this neighbor graph. And then it pulls out the list of atom pairs that are within interaction distance of each other and uses that list to rapidly compute the scores and the derivatives during energy function evaluation. Minimization graph derives from class graph. It may not be surprising. Multi-vec, as I mentioned before, that's a type def for utility vector 1 of real. And a multi-func is a function that takes a multi-vec and returns a real. It defines these two functions, func and defunc. It takes this multi-vec of vars, and that's the func, and defunc, that's the derivative of the function with respect to these vars, and it stores its output in DE vars, and that's how the minimizer algorithm and the function that you're optimizing talk back and forth. And I think I forgot to add the const status of both of these functions, but I think they're there. The minimizer is what uses func and defunc for the multi-vec that it optimizes to walk to a lower energy. And as I said before, there's like a number of different minimization algorithms. I think the latest and greatest is the BFGS minimizer, and I think there's some flavors of that. But it has this nice property of being very fast when you have a large number of degrees of freedom in the system, and that's because it doesn't keep the full Hessian, the n by n matrix of partial derivatives, and so it doesn't spend a lot of time approximating the Hessian either. And it's particularly useful if you're minimizing. There's now a Cartesian minimizer where you have a derivative. I'm sorry, you have a degree of freedom for each dimension for each atom. So 3 times the number of atoms in the system, and that's a very big system to minimize. Yeah.
What's the difference between the Cartesian minimizer and the internal coordinate one in terms of performance?
The Cartesian minimizer, I believe, gets lower energies. It's not easy to do an apples-to-apples comparison because you need to have now a term that penalizes bond stretching and bond vibration. It's, I'm going to say, an order of magnitude slower, but I don't know the Cartesian. I don't know exactly what that number should be. Do you know, Matt, how much slower the Cartesian minimizer is than?
I don't think it's that slow. That depends on your protocol.
Okay.
I actually haven't done it.
All right. So we say it's either 50% slower or 10 times slower. I'm not sure which.
But there are things that in my experience, it's been more like 50%.
50%.
Yeah.
Okay.
There are things that the other one cannot do. Right?
Yeah, I mean, the atom tree minimizer can't get C beta to move, right? So, and my understanding is that we do a lot better at generating native-like structures with the Cartesian minimizer. Actually, I'm going to talk about it on the next slide. This is the third to last slide. Okay, so the atom tree minimizer, that's the one I was just telling you about. It constructs this atom tree multifunc, which derives from multifunc, and then it creates a minimizer and then runs minimization. So that's like the main interface here. And if you run the min mover, I think it's using an atom tree minimizer. Okay, so, oh yeah, no, okay. Yeah, Matt's laptop is not waterproof. No, really, I mean, he's got this bashed-in corner here from Minicon. It's really sad. Okay, so if you implement a new term and you implement the derivatives for those terms, they'll be wrong. And so if you want to, oops. Wow, okay, so there were quite a few more slides than I forgot. Okay, so so if you want to, right, so when you construct a minimizer options argument, you give it the name of the minimizer you want to use, like the LBGFS, Armijo minimizer is one of the latest and greatest ones. You give it some tolerance, which is how little does the score function need to change in order to conclude that the minima has been reached. And so it just, if it hits like a flat region of the energy function, it'll just stop going. But sometimes if you set this really low, it'll hit a flat region and then it'll keep going. So there's advantages and disadvantages of having a large tolerance here. This Boolean value in this portion of the constructor is the flag use neighbor list. That must be true. We do not have any non-neighbor list minimization in Rosetta. And then these last two are deriv check and deriv check verbose, which are flags that say if you want to run the minimizer but make sure that your derivatives are correct, it will do that. And what happens is that the atom tree, so in atom tree minimize, there's like this simple deriv check results class, I'm sorry, this function, simple numeric deriv check, which returns an instance of this simple deriv check results class. And it takes the function at a particular set of values, multifunc, the start vars, the derivatives at the start vars, and then this Boolean of whether or not to send the output to standard out, whether to be very verbose about it, and the number of steps to take. What happens is it computes the partial derivative by like stepping to the left and right of each of the values in the start vars, and then computing a numeric change in the derivative. And so it's very slow. Compares the numeric derivatives against the analytic derivatives, and then its output is of the form of norm and norm numeric. These two values should match. So the norm is the length of the gradient vector, and then norm numeric is the length of the numeric gradient vector. Cos theta is the angle between the gradient vector and the analytic, the analytic gradient vector and the numeric gradient vector in this high dimensional space. And that should be close to 1. And the log norm ratio, which is the log of dividing norm by norm numeric, that should be close to 0. So if you're looking at the output that gets sent to the screen and it doesn't look like this, then your derivatives are wrong. If you want to write an energy function and you get the derivatives and they're working, then you can add these unit tests for your derivatives. There's a class atom deriv validator within the unit test suite that I wrote. It takes a pose, a score function, and move map, and runs a quick numeric deriv check and asserts that the norm and norm numeric values are very close to each other. If you're defining a new scoring term, it's much easier to get the derivatives correct within the unit test suite than it is to try and run minimization, say, in the middle of relax or something, or to write your own application that's just going to test your suite. I'm sorry, your energy function. And it's also it helps me sleep at night, knowing that the derivatives of the e-table still match the e-table function. And so most of the terms, I think in score 12, have unit tests that make sure that the derivatives match. And it's funny how you just make one little modification to your energy function, you don't think it's going to matter, but now the derivatives and the energy function don't match, and then minimization just grinds to a halt and all of Rosetta stops working. So these are very nice things to have. As an example, you can look at the nSmooth energy. So test to make sure that this is one of the unit tests in this suite. So declare pose from trip cage, declare a score function, and set the weight for nSmooth to 0.4. Set the move map so that all of the backbone degrees of freedom are true. And then I create an instance of this atom-derived validator class, give it the score function, the pose, the score function, the move map, and then I do a simple deriv check. And this runs this numeric test, and then just TS asserts that nothing bad has happened. And I added this very recently because I actually had a bug only like a month ago that I fixed where the derivatives were wrong for this term. So if you don't have these unit tests, you can mess things up. Cartesian minimizer, we mentioned it just briefly before. I'm going to say, it's an alternative. Maybe it's 50% slower, but that doesn't seem that doesn't sound like it's a bad thing to me. It uses the F2 vectors in order to get the F2 vectors are the gradient in order to get per atom Cartesian derivatives. So we don't have to change the derivative logic at all in order to use the Cartesian minimizer. That's really great. And then it seems to show great promise in protein structure prediction. It does require that this cart-bonded energy term is active in your score function. Otherwise, it won't respect bond lengths and bond angles, and you'll have awful things happen to your structure. So you need this term on in order to use it. And that's activated if you use this score type. And I think the recommended weight is 0.5 for cart-bonded energy. Okay, and the last thing that I'm going to say is that the Packer, returning it to briefly, there are two parts that do the continuous rotamer optimization. We have the minimization graph that's used. It's constructed so each of the packable residues is going to be a node in this graph, and there are going to be edges. Actually, the whole protein is going to have, each residue is going to have a node in this graph, and the edges are going to be to the surrounding residues. And then I have this class, an atom tree collection, which is responsible for doing the kinematics and derivative logic for a single residue. And then I have one atom tree per residue type that's in the set. And then I have a multi-func that's just going to minimize side chains. And so it gets to cut some corners that the regular atom tree multi-func doesn't get to cut. So it only traverses the edges of the minimization graph incident upon the moving side chains, and it scores and evaluates the derivatives for those edges only. And the minimizer is exactly the same as before. And so I just plug in this SE-min multi-func into the minimizer, and then maybe there's a little extra bookkeeping here, and that's the implementation behind the scenes of these two functions. So if you're interested in sometime in the future of implementing your own minimization-like thing or your own Packer-like thing, this is the last slide. So if you're interested in some of the minimization stuff, I'd recommend taking a look at these classes. And just broadly speaking, I think one of the reasons that the Packer is so successful and that it's used so heavily in lots of different protocols is that it's very efficient in what it does. And its efficiency before was because of lots of very hard coding, at least in Rosetta++. But in Rosetta 3, its efficiency is because it takes advantage of the hierarchical decomposition of our energy function into terms that depend on residues and residue pairs. And so if you have a problem where you want to do a lot of sampling, but say local sampling, so you're just going to maybe move one loop back and forth if you're doing loop modeling, or maybe you've got like two loops that you want to like score against each other. But you don't want to score the rest of the enormous structure that these loops are inside of. Then you can take advantage of the fact that you can evaluate just the interaction energy of your loop with the surroundings, and that would be a very efficient way to score or figure out the change in energy induced by like a movement to that loop. So I hope some of you may, or one of you or two of you in the future decide that you want to take advantage of the hierarchy of the energy types and implement some sort of decomposition of the score function into rapid sampling. Thank you, that's it. Any questions?
That's it.
That's it.